Peng Cheng talking about supersymmetric string vacua with flat backgrounds. So please, Peng, go ahead.
Thank you, Ivor. So first I want to thank the organizers for this invitation. And today I want to discuss a little bit about the effect of flat background on constructing supersymmetric string vacua. And this is going to be based on collaborations with Ilarion and Ruben. And because I don't know how to organize the topic, so I decided to purely discuss about the examples in this talk. So the first example is discrete torsion. First, let's review some basic generalities of two-dimensional conformal field theory. We know that perturbative string theory is formulated on two-dimensional CFTs, and the Hilbert space carrier module over this Virasoro algebra. And if I have a CFT and I have a normal symmetry, I could get it to formulate an IPhT CFT. And the Hilbert space structure of IPhT CFT will consist of several sectors labeled by the group element of IPhT group. And in each sector, we need to select out the neutral state under this IPhT group action. And the perturbation function can be easily written down in this way, and it consists of several blocks with G, H, and G, H belong labeled by the group element of this IPhT group G. Here is perhaps the easiest IPhT CFT example. We consider compact boson with target space a circle of radius r, and then we have a Z2 symmetry which corresponding to the half circle shift. If we get this symmetry, we see that this Z2 action will act on the momentum number and pick up a non-trivial prefactor. And as a result, the projected states will be carrying even momentum modes. And the twisted sector will give us half integer winding number and instead of integer winding number. And overall, of course, this is compact boson CFT with target space a circle with radius r over 2. And then we see that from the construction, there is a natural generalization of construct IPhT CFT, which is first proposed by Wafa, and it's just introduced some non-trivial weights to each block. And after this generalization, we know that modular invariance will impose non-trivial conditions about these weights. And these are the two conditions imposed by modular invariance. And Wafa also proposed a family of natural solutions to it, parameterized by the second group cohomology of this IPhT group. And this set of solutions will be called discrete torsion. And here is an example of discrete torsion. We consider bosonic CFT with target space circle times circle. We could view this CFT as an IPhT CFT by getting the Z times Z symmetry of R times R, two-dimension of R times R bosonic CFT. And then we see that we have a family of discrete torsion given by the second group cohomology of Z times Z. And this is exactly the same as the B-field moduli branch associated with this bosonic CFT. So from this example, we see that the flat B-field background sometimes could be viewed as discrete torsion. Okay, now we can set up our example. I'm going to talk about 5-dimensional flat Seifert manifold. And for simplicity, I'm just going to discuss one specific type of them, which is the Z2 quotient of T5. First, we have 5 copies of circle, and Z2 action acts on the first circle. Z2 action acts on the first of 4 circle as a reflection, and acts on the fifth circle as half circle shift. And it is exactly because this shift that makes the entire geometry smooth. And we will call the fifth circle the Seifert circle. And there are 2 ways of looking at it. Either we locate it as T4 fibered over a circle. When you move one loop around, it picks up involution, or you can view it as a ordinary Seifert manifold. You view it as a Seifert circle fibered over IPhT. And from this description of its geometry, we easily see that if we formulate type 2A theory on this manifold, we are going to get 5-dimensional supersymmetric theory with 16 supercharges. And here the Seifert circle is very important to the geometry of it. It is the Seifert circle that makes the geometry smooth. So the question is, how does T-duality go with this circle? Well, first, let's switch to the CFT perspective. Focus on Seifert circle. We know that the Seifert set 2 will act on the relevant quantum numbers in the following way. It acts on the momentum mode and picks up non-trivial prefactor. And after T-duality, we see that the T-dual version of this Z2 action should act on the winding number and picks up a similar prefactor here. And we can also, and now we can also switch to the, we can also switch to the space-time perspective. Now we consider X5 as Seifert circle fibered over IPhT. We first compactify on the circle. What we are going to see is that we get a 4-dimensional IPhT together with non-trivial GU5 holonomy around each singularity, thanks to the half-circle shift of the Seifert manifold. And then if we T2 the cipher circle, we know that it's going to exchange GU5 and BU5. And if we start with T4 mod Z2, together with non-trivial GU5 and trivial BU5, T0 will give us trivial GU5 and non-trivial BU5. And thanks to the trivial GU5, we see the type 2B geometry is singular, T4 mod Z2 times circle, but with non-trivial B-field holonomy around each singular locus. And although the type 2B geometry is singular, but from the dual 2A analysis, we know that all the singularities shouldn't contribute to the Metzeler's modes at the generic radial circle. So there must be a mechanism involved with this B field that makes all the twisted sectors massive. So the question is that what is the CFT associated with the flat B field background? Well, the answer is discrete torsion. Conformal field theory with target space T4 mod Z2 times the circle could also be viewed as getting the symmetry Z2 times Z of the T4 mod times R CFT. And this time we see that we have a non-trivial discrete torsion. And we have this choice of turning on it, and this discrete torsion is given by this formula. It is very easy to check with the help of this discrete torsion. We find that in the type 2B, we just following the IPhT construction. It's very easy, just include this, I think just include this declaration. And then what you are going to see that it gives exactly the same spectrum as you expected from type 2A side. For example, in the untwisted Z2 sector, we see that the action will act on the winding number and gives the non-trivial prefactor. And also in all the twisted sector, you can easily see that you can pin down the entire perturbative sector of string spectrum, and you can see that they are all massive, although they are associated with space-time singularity. So the conclusion is that with non-trivial discrete torsion turned on, the twisted sector associated with space-time singular locus become massive. And with the non-trivial B field around each singularity, we see that the singular locus doesn't enter into the low energy spectrum. And sometimes singularity doesn't enter into low energy spectrum is called frozen of singularity. And in these two papers, they discuss one specific mechanism of frozen singularity by turning on non-trivial C1 holonomy around each fixed point. And the one we just talked about could be considered as a perturbative mechanism of frozen singularity, and it is related to their mechanism via string dualities. To see that, first we put M theory on cipher times the trivial circle. If we first compactify on cipher circle and T-do the trivial circle, we are going to end up with 2B on this geometry together with C2 holonomy around the singular locus. But if we first compactify on circle and then T-do the cipher circle, what we are going to have is we are going to end up with exactly the same geometry, but this time with non-trivial B field holonomy around the singularity. And now the connection becomes extremely clear. These two backgrounds are related to each other by the SL2Z duality in type 2B. Okay, let's go to a second example, which is perturbative analysis of F theory on FHSV. FHSV is a very special Calabi-Yau threefold, which I'm going to review later. So first, SL2Z and F theory. Type 2B is believed to have SL2Z symmetry, under which in SAS are two forms and axion dilaton charges in the following way. And F theory is a theory makes full advantage of this duality group. And it typically provides supersymmetric string vacua with axion dilaton vary along space-time, which makes it typically non-perturbative. But however, if all the monodromy involved will be just the central element of this duality group, then we see that axion dilaton is not acted upon by it. As a result, we can see that there is a hope of making the string coupling small universally along space-time, and the perturbative description should be possible. And this is indeed the case, and I think the first example was provided by Sen. First, we go to a specific moduli. First, we go to a specific point of this IPhT moduli, and we see that it admits an elliptic fibration, which is T2 fibered over T2 mod Z2, which is P1. And then the monodromy involved will be just a central element of this SL2Z duality, and the perturbative description of it will be just arbifolding the type 2B worldsheet by the following arbifold action. I is referring to the involution on T2. Omega is the worldsheet parity transformation, and FL here is the corresponding to the space-time fermion come from the left-moving sector. Okay, now we go to the FHSV. FHSV is a manifold first introduced into physics literature by Ferrara, Harvey, Strominger, and Waffa, and it is a small elliptic Calabi-Yau threefold given by taking a special Z2 quotient of K3 times T2. And the Z2 acts on the T2 as involution, and it acts on K3 is fixed point free, and it projects out the top holomorphic form, which means that it acts on the middle integral cohomology of K3 in the following way. It acts on the first gamma 1, 1 as involution, and it swaps the two gamma 1, 9. And as for the holomorphic structure, we see that it preserves the Kähler form and projects out the top holomorphic form. Of course, Enric action only exists on special locus of K3 moduli space. And here are some general features of IPhT-TV. First, the action on the elliptic fiber is just an involution, which means that a perturbative description could be possible for this typical F-series vacua. And second, the Enric surface is smooth. Is smooth because the action is fixed point free, and it doesn't emit a spin structure, simply because the Z2 action projects out the top holomorphic form. So what is the worldsheet theory for this specific background? To answer this question, we simply need to find the worldsheet action X corresponding to the central element of this duality group, together with the worldsheet action corresponding to the space-time Enric involution. So here are some hints. First, in the NS-NS-RR sector, it gives space-time bosonic field, which means that these two actions should square to identity in these sectors. And in the NS-RNS sector, that gives space-time fermions, which means that the two operations should square to minus identity. One way to see that is simply because this Z2 action, this Z2 Enric involution projects out the spin structure. And the Enric action, sigma, acts on the worldsheet should give the space-time Enric involution, which means that it should act on the chiral primary operators in the same way as it acts on the cohomology of K3. And as for the action X, first, this field content should be charged under X in the following way. And also remember that according to the construction of IPhT-TV, if we move one non-trivial loop around Enric, B2 goes to minus B2, simply suggests that X should involve the worldsheet parity transformation. Combination of X and sigma is the Z2 action that we are looking for. First, the action X. The requirement that the field content charged under X in the following way, together with the fact that it should involve worldsheet parity, uniquely fixes this action X. It consists of two components that both entered already in stance construction. FL, again, is referring to the space-time fermion number come from left-moving sector. It's also easy to construct sigma. For this, just recall some basic properties of K3 SFT. Okay, first we focus on in the NS-NS sector. The relevant chiral primary operators are the following: the vacuum, which corresponding to identity operator, and we also have 20 quartets. They are in one-to-one correspondence. H here is conformal dimension. I is referring to the quantum number under SU2R symmetry. And they are in one-to-one correspondence with the 20 harmonic 1,1 form on K3. And they're further split into one self-dual quartet, where is the Kähler class, and 19 anti-self-dual quartets. Also, the action on the chiral primary operators can be read out just based on the Enric action on the cohomology of K3. As for the other three sectors, they could be obtained by spectral flow operators. And if we select out the 2,2 superconformal algebra out of the 4,4 one, we see that it has a property that the charge difference, the U1 or charge difference between the left moving and right moving satisfy the following property. The charge difference is an even number in the NS-NS-R sector, and it's an odd number in the NS-R-RNS sector. And based on all these properties, we can easily pin down the structure of this action sigma. And the important piece is the important part is the first one, as the second one will act on the 4,4 superconformal characters. And it is the first one that breaks 4,4 to 2,2. Or space-time, from space-time perspective, it is this part that breaks the hyper-Kähler to Kähler. And we can see that with this, we can see that sigma is indeed the right Z2 action we are looking for. It has all the required properties. It's square to identity in the NS-NS-RR sector, thanks to the charge difference is an even number, and it squares to -1 in the NS-RNS sector. Now we have pinned down the Z2 action on the worldsheet. All we need to do is just arbitrate it and apply standard worldsheet analysis. Here are the key results. First, you see that half of space-time supersymmetry projected out. Space-time supersymmetry is 6-dimension 1,0. And the vacuum is going to give a 1,0 gravity and 1,0 hypermultiplet. Self-Diel-Quartet give a 1,0 hypermultiplet, and 19 anti-self-Diel-Quartet give 9 tensors and 10 hypers. Matches perfectly with F-theory analysis. We can actually also go a little bit further by putting the theory on a circle and TDO it to 2A. And this time the space-time internal manifold is going to be formulated on K3 times S1 mod Z2. And the only subtlety here is just that worldsheet parity needs to be replaced by the combination of worldsheet parity and circle reflection to be compatible with a symmetric GSO projection used in 2A. And the Z2 acts on K3 times the circle in the following way. It acts on X as Enrique involution, and it acts on the circle as a reflection. So as a result, we see that the internal manifold is going to be a smooth, unorientable P- manifold, and the above construction just provide a type 2A perturbative supersymmetric vacua without any extended BPS objects, and formulated on this unorientable P- manifold. And okay, so the topological condition for P plus and P minus structure is the same as the topological condition for orientability and spin structure. It just requires a certain combination of Diffie-Hellman class to vanish. For example, for the P minus structure, oh, this should be P plus. Sorry. Oh, yeah, it's P plus. Good. For P plus structure, we see that it should be second Diffie-Hellman class to vanish. And for P minus structure, it requires the following combination of Diffie-Hellman class vanishes. Okay, up to so far, I only discussed about physics from the worksheet. Now I want to discuss a little bit about the M theory, which means that I have to switch my perspective from worksheet to space-time geometry. Okay, first, more about FHSV. I think the most striking feature makes FHSV so special is that it is mirror to itself. And there is, there is no worldsheet instantaneous correction to the Kähler module space in 2A, compactified on FHSV. One way to realize it is simply because the hyper-Kähler structure is only softly broken in FHSV. And one evidence for the self-mirror property is the following. I mean, this is not a very convincing evidence for the self-mirror property, but it's going to be relevant for our following discussion. So the torsion subgroup of K0 and K1 on FHSV are isomorphic to each other. And also, according to work by Greg Moore and Edward Wheaton, we know that the torsion subgroup of K0 and K1 classifies torsion flat Ramond-Ramond background in type 2A and type 2B. At the same time, they also classify the torsionful difference in type 2A and 2B and type 2A. And in type 2A, the flat are background classified by the torsion subgroup of K0 are generated by the 3 distinct C1 and 1 distinct C3. Sorry, I should replace it by G2 and G4, but it's torsion, so at differential form level, they are all 0. And more interestingly, in this paper, they observed, I think it's written by Ilka Brunner, Jacques Distler, and Rahul Mihajan, I think. They observed that with certain flat C1 turned on, not all the torsional difference labeled given by the torsion subgroup of K1 are allowed to exist in the spectrum. The argument goes as follows. In a specific point of the module space with gravity decoupled, type 2A formulated on FHSV will give us the 4D equals 2 theory with gauge group SU2. And the fact that 2A on FHSV receives no worldsheet instantaneous correction, the space-time implication of that is this 4D equals 2 gauge theory receives no instantaneous corrections. As a result, it has to be finite. The only choice is SU2 with 4 flavors. And by analyzing the Messler spectrum, in this limit, what they observed is that only when certain torsion difference are excluded from the spectrum can this theory be finite. Otherwise, it will give 8 fundamental flavors, which signals the inconsistency of string theory itself. So self-consistency of string theory requires absence of some torsionful difference. In the last page, I want to provide an M theory perspective to justify the observation made in Ilka and her collaborators' paper. First, realize that instead of K theory, the C3 field in M theory seems to be classified by equivariant or differential refined version of integral cohomology. And from M theory perspective, with the presence of the torsion flat C1 will uniquely fix the M theory 7-dimensional manifold, which is a circle fibered over FHSV with a circle fibration given by characterized by this flat C1 background. As a result, once we have fixed the 7-dimensional geometry according to this C1 in type 2A, we can carefully study the lift of K-series class C3 plus C1 in M-series picture. And what we found is that if we analyze the M-series flat moduli space, we see that the K-series class given by C3 plus C1 is actually identical or connected to the K-series class with trivial C3, which means that M-series analysis simply suggests that type 2A moduli branch labeled by two distinct K-series classes are actually connected. Combined with this fact, together with the perfect pairing between torsion D branch and torsion R fluxes, we see that, at least at the torsion level, it seems that the K3 and you shouldn't be able to detect any differences between the K-series class labeled by C1 and C1 plus C3. And as a result, this simply imposes a condition on the torsion D branch which satisfies the following property. And it is exactly this property that gives you exactly the same physical D branch that already been observed in the paper that to satisfy the self-consistency of string theory itself. And of course, this example leads to lots of problems. For example, what is the right way to characterize a moduli of flat background? And how to reconcile the fact that the flat background in type 2A and in M series are actually classified by two different cohomology series. And these problems are currently under our investigation. Thank you very much.
All right, thank you. All right. Okay, now it's what? Question.
Thanks for the nice talk. I wanted to ask about the last piece. So will you have this consistency condition on the alpha on the torsion D branes?
Yes.
What's the M-theory interpretation? Is that they're wrapping something which is actually trivial in homology, and then they can unwrap, but you don't see that on the base, or?
You mean what is this one?
Yeah. That condition can be interpreted just geometrically in M-theory?
Yes. You
It's
mean
just
that
that
what's the physical condition counterpart to this one? This is purely some algebraic topology.
Can you say?
Your question is what is the physical
Yes.
problem?
Yeah.
Well, I mean, this is very subtle, because if you apply, you see that Frieda-Witten anomaly already vanishes in this case. So it's, I mean, even Frieda-Witten anomaly, it doesn't help. So this case, I don't know, at least for the physics. It's not clear.
But I was asking, is the picture that the torsion D branes that are wrapped on those cycles are actually unstable and can be unwrapped, or is just inconsistent to have those D branes?
No, it's not. I mean, I hope it's inconsistent. But
you think it's inconsistent? Okay.
But I'm not sure, because the only inconsistency condition is Frieda-Witten anomaly, but it satisfies the cancellation of Frieda-Witten anomaly. So.
Okay, thank you.
Over there.
Hi, thanks for the nice talk. My question is also on this slide. Are these circle fibrations over the FHSV manifolds? Is this one of Joyce's G2s?
No.
No. Okay. I see. All right, so I guess it'd be like a new one per se, or
a U1? Yes, a U1, just a U1.
Oh, no, I said a new G2, I guess.
This is the holonomy is SU3, still SU3. The circle is flat.
Oh, I see. Okay. All right, sure. And so the statement of the C3 being possibly classified by equivariant integral cohomology. So one sort of like thing pointed out by like triples, fluxes, and strings is that, you know, if you have like these frozen singularities, like in some sense, the C3 is like almost like a subset of the equivariant. Yes.
Also that Also they proposed one consistency condition about this D branch together with these Raman fluxes, but that one is too strong. It's not the right one.
Sure, I see.
For example, in this analysis, if you impose their conditions, what you are going to end up with 4 adjoint flavors. This again signals the inconsistency of string theory itself. So that one is too strong.
Okay. All right, thanks.
Any further questions? Looks like there are no any further urgent questions. So then let's thank Peng again.
Thank you.